Okay, so the following lesson builds on a lesson that we've previously learned, which is how magnetic fields are produced by current passing through a conductor. We're looking at section 13.4, the magnetic field of a coil or solenoid. Recall from the previous lesson that as current passes through a straight conductor, it produces a magnetic field around it. The magnetic field is circular around the conductor. And as you recall, we have the right-hand rule number 1, right? Which is that if the thumb is in the direction of the current, then the fingers point in the direction of the magnetic field. So let's take a look at what happens if we make that conductor into a loop. And let's take a look at the following diagram. Well, if this right here is the conductor, and I have current coming out, and I wrap my fingers this way, well, that means that my magnetic field is going this way, as denoted by the lines. But you can see that as the conductor curls, it causes the magnetic field lines to bunch together, which actually produces a very strong magnetic field in one direction. And that's what we say right here. When we bend the conductor into a loop, the magnetic field intensifies, and that's because, and again, if we do the right-hand rule onto the other side, well, it's still, we have this right here, and so as you can see, we have a strong magnetic field that passes through the center. What happens if we bend the conductor into a series of loops or a coil? The coil itself is called a solenoid, and for that, it's just a series of right-hand rule number 1, which is, if you take the current and you put your thumb in the direction of the current and you use your fingers to do circles around it, well, if we have a new right-hand rule for a coil, and that states the following, okay, which is, if we, sorry for the bent paper there, but, okay, so if we put our fingers in the direction of the current around a coil, our thumb indicates the direction of the magnetic field. So let's write that there on the box. Okay, so the right-hand rule for a coil states that, okay, fingers in direction of current, thumb in direction of magnetic field. This is just a summary of what you'll find in your textbook. So let's read this right here, which I pulled from the textbook. At both ends of the coil, the field is still strong, but at the sides, the field is weaker as the lines begin to bend and spread out. So inside the coil, we have a very, very strong magnetic field, and outside, it's less strong. So as you can see here, the magnetic field on the inside here is quite strong, especially, and even at the ends, it's strong. And then it loops around and gets a little weaker on the outside. So let's read the following now. Think of the coil as a bar magnet, and the magnetic field should make more sense. So if we think of this coil right here as a bar magnet, well, look at our field lines. They're going from south to north, which, if you remember our field lines are supposed to go from north to south, but that's only on the outside of the magnet. So inside the magnet, the field lines go from south to north. So just like over here, we have field lines that are moving from south to north inside the magnet, closing these loops. Well, the same thing is the case in a coil. The field lines go from south to north on the inside of the coil, and then on the outside they go from north to south. Now, if we put an iron core in the middle, then all the domains of the iron core will be affected by the magnetic field produced by the current, the magnetic field produced by the coil, and they'll all point in this direction. So let's read figure 5 here. The ends of a coil can be thought of as the North Pole and South Pole, and the field within the core resembles the field in the interior of a bar magnet, with its ferromagnetic dipoles aligned so they will point in the same direction. Okay, so the take-home message here is that when you have a coil and you have electricity or an electric current passing through the coil, so your fingers are in the direction of the current, your thumb points in the direction of the magnetic field on the inside of the coil. Okay, so your thumb is pointing this way, so on the inside of the coil we have the magnetic field going from south to north, and then on the outside of the coil looping back around. Jumping to the next page, if we look at the first example, if we wrap a wire around an iron core, remember what I said, the magnetic field produced by the current will cause the domains in the iron core to all align and produce a magnet. So, determine the direction of the current in the wire. So, as you can see here, it gives us that north is this way. So that means that the magnetic field lines on the inside of this coil are pointing this way. So if the magnetic field is pointing this way inside the coil, then that means my thumb should point this way and my fingers should therefore wrap this way. So I do the lines this way and up. So here I've answered the question. I've determined the direction of the current using the right-hand rule for a coil or solenoid. Example 2. Wire is wrapped around an iron core. Determine the north and south pole of the solenoid. Well, it looks like they don't give you enough information here to answer the question, but in fact they do. We have to recall that the short portion right here is our negative terminus of the cell, and this is the positive terminus of the cell. We're using conventional current, so that means positive to negative. That means that it's going this way, and therefore this way. Okay, and coming in this way. All right, so again, I have current going downwards this way on my coil. So my thumb points in this direction. This should be the north and south poles of the solenoid. Okay. My fingers wrap in the direction of the current, and my thumb in the direction of the magnetic field. So there are a number of factors that affect the strength of the coil, and we have proportionality statements here. So B, which is the magnetic strength, or the strength of the magnetic field, represented by B, is directly proportional to N, where N represents the number of loops within the coil. So the more loops within the coil, the stronger the magnetic field. So if I loop it around more and more times, I'm going to get a much stronger magnetic field. B is proportional to I. Well, we recall that I stands for current. So as we increase the current, we increase the magnetic field. And B is proportional to mu. So the final thing we're going to look at is field strength, which is B is proportional to mu. B is proportional to magnetic permeability. So certain substances that are placed within the coil can be magnetized much more easily than other substances. So as we can see here, iron has a much stronger magnetic permeability than air. So the field strength will increase much more strongly if we have an iron core versus if we just have air in the middle, right? And so that again relates to mu, which is magnetic permeability. We use electromagnets for a lot of different things. Lifting magnets, so in junkyards, being able to lift large pieces of metal using electromagnets, electric bells, speakers, motors, lots of applications that we will take a look at. If you could also take the chance now and read through section 13.4, which is pages 482 to 489. It will give you some more information that might supplement this lesson. Finally, there is a problem set that I attached to this lesson. If you could also complete the problem set that has to do with the right-hand rules for a straight current and the right-hand rule that we just learned for a coil. Okay, so your homework is the problem set, which is attached on right-hand rules.